Hello again. The first video in this series, Understanding Computers, Smartphones, and the Internet, explained the fundamental simplicity of how computers work. It demonstrated how code written in a computer programming language needs to be compiled into simpler machine code instructions. In fact, there are only 4 types of machine code instructions: move data, shown in yellow; jump to another location in the program, in green; calculate, in blue; and the 4th type of instruction is not shown in this example because they are special instructions that are reserved for the operating system and cannot be used by an application program. This simple set of machine instructions is the basis for all computers, smartphones, and custom computers in use today, and computers being designed for the future, such as robots, self-driving cars, and spacecraft. Now let's look at computer hardware in more detail. At the electronic level, machine instructions are designed using logic gates. All the machine instructions in the CPU can be built using combinations of only these 7 basic logic gates. If you ever took a course in logic in philosophy or mathematics, or a Boolean algebra course in computer science or engineering, you will be familiar with these logic functions, but the symbols and notations may be different than shown here. The fact that machine instructions can be designed with these few logic functions was shown in 1938 by Claude Shannon. He published a paper which proved that electrical switching circuits could solve all the logic problems that Boolean algebra could solve. His paper provided diagrams of several circuits, including a circuit that could add numbers. This ability of electrical switches to implement logic underlies the design of all electronic digital computers. We will show an example using just 2 logic gates. First, let's look at an AND gate. It has 2 inputs, A and B, and an output, AB, which is the result of the logical AND of the inputs. If you say that A and B are true, that means that both A and B are true. So if you said that Angelina and Brad came to dinner, this would only be true if both of them came to dinner. If either one of them did not come, then your statement would be false. A truth table defines the AND logical function for all possible cases. It has all the possibilities for A and B, a total of just 4 combinations. 1 represents true and 0 represents false. The highlighted row in this table contains the only true statement. All the other rows are false. In an electrical circuit, true represents a current and is indicated by 1. False represents no current and is indicated by 0. So, current flows through an AND gate only if there's current at both inputs. Let's look at one more logic gate. XOR is exclusive OR. Exclusive OR is true when either A or B, but not both, are true. Here's the symbol for an XOR logic gate and its truth table. So, current flows through an XOR gate only if there's current at either input, but not both. Now, the rather amazing thing about these 2 simple logic gates is that you can use an AND gate and an XOR gate to do arithmetic. Here is the logic designed for an add instruction that adds 2 binary digits, A and B. A and B go through an XOR gate to produce the sum, and also through an AND gate to produce the carry over to the next column. The addition table at the bottom shows all the possibilities of adding 2 binary digits, A and B. Remember that a binary digit can only be 0 or 1, so there are only 4 possibilities. The first 3 lines are simple arithmetic. For example, in the first line, 0 plus 0 equals 0, 0. In the 4th line, 1 plus 1 equals 1, 0, which is 2 in binary. Machine instructions for addition are generally needed for numbers that contain more than 1 binary digit, called a bit. To design an instruction that adds 2 32-bit numbers, you can use a sequence of 32 binary adders, slightly more complicated than this one, where the carry output from the adder for the first binary digit is input into the adder for the second binary digit, and so on. This completes our introduction to circuit design. Remember that the other part of Shannon's thesis was that these logic circuits could all be made with simple electrical switches. During his time, switches were made with mechanical relays, similar to the switch that you use to turn a light on and off. In our time, switches used in electronics are made with transistors. Here is the standard diagram for a transistor. There is an electrical voltage differential between the plus voltage and the ground, so a current can flow between them. But there's no current at in, so the vertical bar in the transistor is not conducting and no current flows through to out. So in this case, the transistor is off. Now, if a current is applied at in, the vertical bar conducts electricity, the transistor switches on, and current flows through to out. Now that we know how a transistor works as a switch, let's see how it can be used to construct a logic gate. The right-hand side of this diagram shows an AND logic gate that is made with two transistors that are connected so that the output of the first is input to the second. There must be current flowing through both of the inputs A and B into the transistors for current to flow out. This is the case shown and reflects the highlighted line of the truth table. Now, if the current at B is turned off, then the second transistor is switched off and there will be no current going out, as per the third row of the truth table. So an AND logic gate can be built with two transistors. Similarly, transistor circuits can be built for all the other basic logic gates. This is the basis for the hardware design of a CPU. In the next video in this series, Part 3, Understanding Computers, Smartphones, and the Internet, we will show how transistors are built in silicon chips and why they are so important to the high-tech industry.